All right, hello, good morning. We have bells, which is nice, so that way, we get started on time. Um, Plus, it really makes you feel like you're at school when you hear that sound of the bell. So I have a do now up. I'll have, just like normal, I'll have a do now up every day. Remember that today is Tuesday, so you can write none, no school, Thanksgiving break, under Monday. If you did not pick up a do now sheet last week, you can just use a blank piece of paper and set it up just like the do now sheet. So you have Monday, Tuesday, Wednesday, Thursday, Friday, and then next week you can always just use the back of that piece of paper if you want. But for the do now, just two questions. One is reviewing chromatography and one is reviewing types of solids. So take just a minute or two, see if you can answer these questions. So for the number one, you're just explaining how chromatography works to separate mixtures of liquids. And I gave you a hint. I said review the background information from the lab. And then for number two, you have an unknown solid. How could you use the properties of solids to determine the type of bonding that exists? So how could you tell if it's ionic or metallic or molecular or covalent network? So take just a minute or two, try to answer these questions, and then we will go through and talk about the answers and why these types of questions are important. So just take a couple minutes, try to answer these, even just come up with, maybe a couple words that might be useful for each one of them. All right, so before we go over the answers, notice I just put the bell schedule up here. Our class times are still the same, but fifth period, just in case you didn't see the schedule, fifth period is 10:35 to 11:25 for everyone. So if you normally eat a lunch, you're not. Lunch is at 11:25 for everyone, and then we go back to sixth period. So for number one, for paper chromatography, this is the lab that we did last week. We can separate mixtures of liquids based on attractions and polarity. So you don't have to write this entire paragraph. If all you do is write down what's bolded and underlined, you're okay. So you separate a mixture of liquids based on attractions and polarity. So the attraction between the mixture and the solvent that moves up the paper, and between the mixture and the paper itself. So just to do a quick review of chromatography, remember that capillary action draws the solvent, which is the mobile phase, up the paper. And if the component of the dye, or the mixture, which for us was dye, if it's attracted to the solvent, it moves up the paper with the solvent. So for us in the chromatography lab, the blue dye moved really far up the paper. That meant that it had strong attractions to the solvent. If it has more strong attractions to the paper, then it's going to stick to the paper and it's not going to move as far. So the attractions and the polarity are based on what the mobile phase is, because for us, the mobile phase, the solvent was NaCl dissolved in water. So it's very polar. The paper was not as polar. So that's how you can look at polarity. If you have your solvent is something like hexane, which is C6, which is C6H6, right? And it moves up, then that's nonpolar. So that means whatever moves up the furthest is also nonpolar. And then for number two, with properties of solids, one thing you could do is test conductivity. So the reason that I put both of these questions up here is because we have seen both of these questions as both multiple choice and free response questions. This conductivity question has shown up on the practice test every year for the last 6 years. So when you're looking at types of solids, you can test the conductivity, because if it conducts as a solid, it's metallic. So metallic solids are the only ones that always conduct electricity. If it does not conduct as a solid, but it conducts as a liquid or as a solution, then it's ionic. This second sentence about ionic solids is always what we see. So if it doesn't conduct as a solid, but then you melt it down as a liquid, or you dissolve it in water to form a solution, and it conducts electricity at that point, then it's ionic. And then molecular and covalent network, they differ in terms of conductivity. So conductivity for sure allows you to determine metallic or ionic. I want to go through and kind of review one part of the video. And the reason that I want to go through and review it using models that I have is because we again have seen questions like this on the multiple choice and the free response section of the AP test. So what we're going to do is we're going to focus on the solution process. So on page 2 of the notes, there is right up at the second part down from the top, it says NaCl dissolving in water. And it talks about the forces between the ions and water and forces that must be overcome. And so I want to show the solvation process of sodium chloride and water using the little models of NaCl and of water that I have. And as we're using the models to show this solvation process, if you did not yet draw this in your notes, you can do that. But then I also want us to be thinking about the energy required for each of the steps, whether it's exo or endothermic, so whether energy is required or released, focusing on also orienting the waters in the correct way, so looking at correct orientation. And then we're also going to look at labeling important forces in our diagram. So a few different things that we're going to be focusing on. And so what we're going to do is we're going to look at models that I have, and I have it on the document camera. So I'm going to share with you the document camera view. And so we've seen these models before, right? These are NaCl, so I have Na plus and Cl minus. So the reason that I know this is Na plus is because cations are always smaller. Anions are larger because cations, you've removed electrons, resulting in a smaller atomic radius or ionic radius in this case. And for Cl, you've added an electron. And so electron or electron repulsion makes the anion a little bit larger. So what I've showed here is kind of like a lattice. So we have two NaCls. So I'm going to focus on if we just had one NaCl here. So I have Na plus attracted to Cl minus. Remember that anionic bond right here is simply an attraction, right? It's just an electrostatic attraction between the positive and the negative ions. And then I have water molecules surrounding my Na plus and Cl minus. So what I want to do is I want to look at what is required in terms of energy. So right now I have an ionic bond right here. So with this ionic bond, just like if I had this ruler, right, and I wanted to try to break the ruler, I have to put energy in. So to break any attraction, whether it's an ionic bond, whether it's a hydrogen bond, whether it's dispersion forces, to break an attraction, it takes energy. So it's going to take energy for me to separate these. So that was endothermic. I had to put energy in to separate these. Now you'll notice around here I have water molecules. Well, remember that if I have these two water molecules here, they are attracted by a hydrogen bond, right? It's an intermolecular force. To overcome this hydrogen bond, it takes energy. So it takes energy to separate the solute. It takes energy for me to separate all of these solvent molecules. So it takes energy to separate anything. Now, when I want to form the solution, what's happening? So this is Na plus. So if I think about water, oxygen is partially negative, hydrogen is partially positive. So if this is Na plus, notice if I try to put the hydrogen near it, it's actually not attracting. It's repelling a lot. If I put the oxygen side near it, it's attracted. And so what's going to happen is these water molecules are going to come near Na plus. Of course, this is also magnetic. So notice only the oxygen side is attracted. So what I have here is I have my Na plus surrounded by what's called the solvent cage. So what I'm going to do, I'm going to just add a little label here. All of these water molecules surrounding an ion is called the solvent cage. Now, if you notice, I can only have 6 water molecules around it. The solvent cage consists of 6 water molecules. And in terms of the orientation, oxygen is oriented near Na plus because you have a positive with Na plus and a partial negative with oxygen. Now, if I did the same thing for Cl, so here's my chlorine. I'm going to just hold it up. If I try to bring the oxygen near it, it repels because oxygen is partially negative and chlorine is completely negative. The hydrogen, however, the hydrogen is attracted to the Cl minus. Now this is a little bit easier to see the solvent cage. So if I kind of turn this, notice how you have 4 water molecules surrounding, 1 on top, 1 on bottom. There's the solvent cage. Now the other thing that I want us to think about is the attraction between the water and the ion. So when you have an ion, Na plus, Cl minus, K plus, NO3 minus, you have any ion attracted to a polar water molecule, this results in ion dipole forces. Again, the reason I'm showing you this as a model is because this was a question on the free response a couple years ago where you had to orient the water molecules correctly around an ion. So if it's Cl minus, the partially positive hydrogens are going to surround the Cl minus. If it's Na plus, the oxygen will orient itself toward the positive Na plus. But remember that with these water molecules, it's not completely positive hydrogen or a completely positive oxygen like it is with ions here. These share the electrons, so that's why it's just partially negative and partially positive. So again, that is part of the hydration process for NaCl under or on page 2 of the notes. So before we get into the next part, any questions on looking at those models and looking at the hydration process? No? Okay, so examples 1 and 2 were actually in the video. So on page 2 of the notes, examples 1 and 2 were in the video. So you'll find that there are some examples that are in the video embedded as questions. Other ones we'll be doing together. So examples 1 and 2, if you did not write those down, you can go back into the video and double check the correct answers for looking at what intermolecular forces must be broken and what are going to be formed. So the next thing that we're going to actually do is we're going to go through examples 3 and 4 together. Now, for us to go through them together, we're going to do this a little bit differently because I want to give you guys the opportunity to answer these questions as well. But we're going to do it in a little bit different of a way because I want everyone to be able to answer the questions, but not be, scared to answer them like in the chat. So instead, we're going to use something still with Google Slides, but something that's going to allow you guys to actually answer the questions as well. And so to do this, you will need a new tab in Chrome. So you can leave the Google Meet open so that you hear what I'm saying to you, but anything that you will need will be on the slides when you open a new tab. So I'm going to let this load. I'll share my screen with you so that you can see exactly what you'll need to do. And then what we'll be doing is we'll be going through each part of the examples one by one. I'll make sure that you have the correct answers so that you can fill it into your notes. So what you need to do is you need to, so again, open a new tab in Chrome and go to joinpd.com. So you'll go to joinpd.com and then the code is right here. So XRZHEC. And I can also put it right into the chat for you as well if you want to just click on the link. So you also can just click on that link that I just put into the chat. It will ask you to like log in with Google. So just log in with your school account, and you'll be answering all the questions anonymously, but then I'll be able to see like who participated. And so my goal is to give you guys like a participation, like almost like the do nows, where you get like this participation like grade kind of throughout the week, just to keep everybody engaged, and to give you a reason to stay engaged. So again, joinpd.com, or you can just click on the link. If for some reason it like kicks you out, you can go through and just rejoin. And essentially what we're going to do is I'll start in just a second, and it's just going to ask you questions. And so I know the example, for example, example 3, that was a lot of examples, is 4 parts. And to you on your notes, it looks like it's short answer, but it's actually going to be multiple choice on here. We'll talk about the right answer, and then you'll be able to write that correct answer down. So you can see on here for this first part of the example. So for example 3 is at the bottom of page 2 of your notes. It says, for each of the following mixtures, describe what types of intermolecular forces are dominant in the attractions between the solute and the solvent. So you have turpentine, which is C10H16, dissolved in toluene, which is C7H8. So what you're looking for when you're looking at the type of intermolecular forces that are dominant is you are looking for what they have in common. So you want to see, what does turpentine and toluene have in common? So you have 2 hydrocarbons. So think about what they have in common, and just click, the multiple choice answer that you think. So I have dispersion, dipole-dipole, hydrogen bonding, and ion dipole forces. So choose which one you think is the most dominant attraction between solute and solvent. So it looks like we have 16 responses so far. And what I'll actually do is I will I'm going to actually lock the screen. I'm going to talk about it, and then if you want to go back and change your answer, you can. So I'm going to just lock it right now. I'm going to show the responses. So it looks like most people chose dispersion forces, which is correct. So I'll unlock. So if you want to change to dispersion. So the reason that it's dispersion, you're looking for what they have in common. So turpentine is a hydrocarbon. Toluene is a hydrocarbon. If you actually look at the Lewis structure, they both are perfectly symmetric. They have no dipole moment, so there's no electronegativity differences. They're both dispersion, and so that's going to be the strongest solute to solvent attraction. Good. So make sure I forgot we have bells. We'll go through this, and then I'll give you guys like a quick 5-minute break. So for the second one, so bromoethane, which is CH3CH2Br, dissolves in acetonitrile. So you have CH3CN. So I tried to give you at least the formula so that you can see. So again, you're picking which one is the strongest solute to solvent attraction. So bromoethane is the solute because it's being dissolved. Acetonitrile is the solvent. So pick which one of those you think that bromoethane and acetonitrile have in common. And again, you can see when I show the responses, we don't see who chose what. So like if I show your responses right now, right, it looks like a majority chose dipole-dipole, some chose London, some chose hydrogen bonding. So if you chose dipole-dipole, That's the correct response. So it's dipole-dipole because there is no hydrogen covalently bonded to NO or F. Remember, for it to be hydrogen bonding, you have to have hydrogen covalently bonded to NO or F, attracted to NO or F in another substance. So yes, acetonitrile does have the N, but it's bonded to a C, and there is no H covalently bonded to NO or F in bromoethane. So you have the Br here. This results in electronegativity difference because CBr is a polar bond. Acetonitrile, you have this N, which is actually triple bonded to this carbon. And so this N is going to carry a much higher partial negative charge because it has a high electronegativity difference. So for part 2 of example 3, you should have chosen dipole-dipole forces. So for part 1, we had dispersion. Part 2, we had dipole-dipole forces. So for part 3, we have acetic acid, which is CH3COOH, dissolved in water. So what would be the most dominant intermolecular force between acetic acid and water? So you want to look at what they both have in common. Good. We already have 17 responses. If we look at these, good. So it looks like a majority chose hydrogen bonding, which is correct. So hydrogen bonding is what you want to make sure you have written down for part 3, because acetic acid, you have this OH here. So you have hydrogen covalently bonded to O, and then water also hydrogen bonds. So you can actually have acetic acid hydrogen bonding with water. So the solute-solvent interaction between acetic acid and water is very strong because you have hydrogen bonding. And then finally, for part 4 of example 3, you have potassium nitrate, which is KNO3, dissolved in water. So the solute is potassium nitrate, the solvent is water. So what type of intermolecular forces are dominant? Okay, so we have kind of a spread of answers here. Right, so think about what, first, water is polar, right? So water is polar, so we're either looking at, well, I guess that's not necessarily true. If we had something like CCl4 in water, the only thing that they have in common is dispersion. But remember that water is polar, water has a potential to hydrogen bond. And so potassium nitrate, KNO3, that's ionic. So that's going to be like NaCl, right? NaCl is ionic, breaking apart. When KNO3 breaks apart, it breaks apart into ions. And so ion dipole forces are what we would see in this example. So for part 4 of example 3, you should have ion dipole forces. So I'll read through just to make sure you have them written down in your notes. So part 1, dispersion. Part 2, dipole-dipole. Part 3, hydrogen bonding. Part 4, ion dipole. So you're looking at what do they have in common? What type of attraction would they have with each other? So then if we take a look at example 4, I'm going to pause here. If you want to like get up away from your computer and just walk around for a couple minutes, you can. However, on this is going to require you to type. So I want you to just start by answering part A. So once you get up, walk around, I want you to just answer part A to start. So this, you can tell this is from an old free response question. Using this information, answer part A. So identify a compound that's nonpolar and justify your answer. So I'm going to give like 4 minutes for this because I want you guys to be able to take a break if needed. And then at about 8:30, we'll talk about part A and then we'll look at part B. So once you've answered part A, you can answer part B either in the same box or you can add another response to answer about ethanol and ethane thiol. So ethanol is CH3CH2OH, the third one down. Ethane thiol. So when you see the word thiol, THIOL, that means that there's a sulfur. So ethanol, that OL means it's an alcohol, which means it ends in OH. Ethane thiol, instead of ending in OH, ends in SH. So just a quick thing with organic. That's definitely more of an organic aspect. So you're looking at why ethanol is completely soluble in water, but ethane thiol has limited solubility. So why does ethanol dissolve in water much better than ethane thiol? And it says account for the difference in solubilities between the two in terms of IMFs. So make sure you're talking about the intermolecular forces that exist in ethane thiol and the ones that exist between molecules of ethanol and water. So you're looking at ethane thiol in water versus ethanol in water. See a lot of people with their answer to A looks good. We'll talk about the reasoning for A because AP was looking at specific reasonings, but it looks like pretty much everyone has one of the two correct nonpolar substances. I see some people for B. Good. They're talking about the difference in intermolecular forces. Right, good. So I see a lot of good responses um, for both A and B. I'm looking through everyone's responses on my other computer. Um, so there's going to be a lot of, if I put the responses, I will see a lot of different responses. I just want to read through some that I just starred as I was looking through for these responses. So one of them, ethane is nonpolar because it's symmetrical. Good. Ethane is nonpolar because there's no pole towards any direction. It's even around the molecule, which is good. You're talking about dipoles. Another one says ethane is nonpolar because its molecular structure does not have any dipoles, which is good. The other one that you could have chosen for the exact same reason was ethyne. So both ethane and ethyne, CH3, CH3, and C2H2 are both nonpolar. So whichever one you picked, whether ethane or ethyne, those are both nonpolar because of the structure itself. So whether you talked about there's no dipole moment, whether you talked about it being symmetric, either one of those works. And then for part B, ethanol is completely soluble in water. So why? We want to account for these differences. And so one of them, one response I saw said ethanol can form hydrogen bonds with water. Ethane thiol cannot. So the stronger attraction due to the hydrogen bonds cause ethanol and water to mix. There's another one, ethanol is hydrogen bonding, where ethane thiol has dipole-dipole. The difference in the strength of the intermolecular forces makes the difference in solubility because hydrogen bonding makes ethanol more soluble. So a lot of good responses here. So just to make sure that we're getting correct justifications, that's going to be the important thing with AP. I want to make sure that you get everything added to your notes. So example 4 was at the top of page 3 of the notes. And so for this, for part A, you could have said ethane or ethyne. Those are nonpolar. And it needs to be because of symmetry or there being no dipoles, right? Or no electronegativity difference. If you justified by saying it's all C's and H's, you need to make sure that you talk about symmetry or no dipole moment, right? Or, electrons are shared evenly, something like that. So for part A, make sure that you write something down about symmetry. And then for part B, like I read some people's responses, ethanol is able to form strong hydrogen bonds with water, whereas ethane thiol does not have that similar capability because, as people said in their responses, ethane thiol only exhibits dipole-dipole forces. So although ethane thiol exhibits dipole-dipole, it does somewhat dissolve. That's why it has limited solubility. So the formation of hydrogen bonds increases the attraction between molecules of ethanol and molecules of water, making them more soluble in each other. So again, ethanol can hydrogen bond, ethane thiol can only exhibit dipole-dipole forces, which is why it can still dissolve because water exhibits dipole-dipole forces as well, but ethanol will dissolve more, right? So again, you want to make sure that you get that information added into your notes under example 4. And then after we go through, like after you get this written down, we're going to actually flip to page 4 in our notes. And instead of having you do this at home, like on your own, we're going to actually continue on with using Pear Deck. And I'm going to actually have you try this. Again, the thing that I like about this is that you can, try, and if you get it wrong, you fix it. And so where if I just asked you to do this on your own and check your answers, then it might not be as useful. So again, we're going to flip to page 4. So page 4 says solubility, polar versus nonpolar. It looks like this. And we're only doing 2 rows at a time. So what we're doing here is we're looking at what solvent will this solute dissolve in. So you have check marks. you're going to drag the check marks. Now, some solutes can dissolve in multiple solvents. So up at the top, you have the information, right? Remember that we can use like dissolves like. That's not our reasoning that AP wants. We always need to talk about attractions, but it's an easy way for us to think about it. So polar molecules will dissolve other polar molecules and ionic substances. So polar will dissolve polar because of dipole-dipole forces, hydrogen bonding, and ionic due to ion-dipole forces. Nonpolar will dissolve other nonpolar. And alcohols, I actually put a picture of, this is butanol. It's an alcohol. I put a picture of the Lewis structure of butanol on the slide so that you can actually see what it looks like. But it says alcohols have characteristics of both polar and nonpolar, and they will dissolve both types, both polar and nonpolar substances, but not ionic. So you can notice you have all these C's and H's. So you have a large portion of an alcohol has London dispersion forces, and then you have some that will exhibit hydrogen bonding. So I want you to try 1 and 2. So figure out what solvent. You could put multiple check marks, but I want you to try and see. Okay, remember that ionic salts, so like NaCl, ionic can only dissolve in polar substances. Right, so ionic, NaCl, can only dissolve in polar substances. So to give a hint, you should have 1 check mark for NaCl, and you should have 2 check marks for I2. So again, a little hint. 1 check mark. I see people's little check marks moving. 1 check mark for NaCl, 2 check marks for I2. And again, read at the top if you need to. It talks about what will dissolve what. Good. So it looks like most people had fixed it for NaCl. NaCl can only dissolve in water. So for NaCl, you should have 1 check mark under water, and that's all. NaCl will not dissolve in CCl4. NaCl will not dissolve in an alcohol. I2 is nonpolar. Iodine is nonpolar. So nonpolar substances will dissolve in nonpolar solvents and can dissolve in an alcohol. So for I2, you should have a check mark under CCl4 and alcohol. Good. And I'll put the answers up on the last 2 slides just in case. But from what I see, it looks like everybody had those correct check marks. So let's look at ethanol and benzene. And I gave you the formula for ethanol. Ethanol is an alcohol. And then benzene is C6H6. So you want to start by looking at, is the solute polar, nonpolar, or ionic? And then that will help you figure out where it will dissolve. So you should have 5 check marks that you can move. I'll give you a hint. You will use all 5 check marks. All right, so you will use all 5 check marks. Let's see. It's changing so quickly. Good. Paul, I see yours looks good. Abby looks good. Yep. Mara looks good. Yeah, so remember that ethanol, right? Ethanol is an alcohol. Alcohols exhibit both polar and nonpolar characteristics, which means that alcohols like ethanol will dissolve in both polar and nonpolar solvents and other alcohols. So ethanol should have a check mark under each solvent. Ethanol will actually dissolve in all 3 because it has similar properties to all 3. Benzene is nonpolar. So if benzene is nonpolar, it will dissolve in other nonpolar solvents and in alcohols because alcohols exhibit nonpolar aspects as well. So benzene will dissolve in CCl4 and alcohol because CCl4 is nonpolar. So in terms of these solvents, you have water, which is polar, CCl4, which is nonpolar, and alcohols, which exhibit both. So you should have all three checked for ethanol. You should have CCl4 and alcohol checked for benzene. Then let's look at Br2 and KNO3. So Br2, hopefully you can look back at ones that you've seen. Br2 and I2 are similar. Similar properties, they're both halogens, they're both diatomic. And so just to give you a hint, you should only be using 3 check marks here. Good. Carter looks good. Nathan looks good. Lacey, good. Yeah, so Br2 is nonpolar. So remember that nonpolar solutes will dissolve in nonpolar solvents and alcohols. So Br2, you should check mark CCl4 and alcohol. KNO3 is ionic. Ionic will only dissolve in polar substances. So KNO3 will only dissolve in a polar substance like water. So for KNO3, you want to make sure that you have your check mark under water. And then the last two, we're going to look at toluene, which is C7H8, and calcium hydroxide. So again, you want to think about the solute. Is the solute polar, nonpolar, or ionic? And then based on the solute, how would it dissolve? So just to give you another hint, you're only going to use 3 check marks. You're going to use 3 check marks. So toluene is going to be similar to benzene. Right? They're both similar in terms of structure, in terms of properties, in terms of intermolecular forces and polarity. Calcium hydroxide, you have to think about calcium hydroxide. Good, Emily, Abby, Ashley, good. So toluene is nonpolar. Toluene is a nonpolar solute, so it will dissolve in nonpolar solvent like CCl4 and in an alcohol. CaOH2, calcium hydroxide, is ionic. Calcium hydroxide is ionic, so it will only dissolve in a polar solvent like water. So for toluene, you should check CCl4 and alcohol. Calcium hydroxide, you're going to just check water. So here are the correct answers. You can just double check, make sure that you have them. I know I did X's, check marks are the same thing. So for NaCl, you checked just water. Iodine was CCl4 and alcohol. Ethanol was all 3. Because remember that the solute is what gets dissolved. The solvent is what does the dissolving. So for this solvent, you had 3 solvents. You had polar, nonpolar, and then an alcohol, which exhibits both. And then benzene and Br2 are both nonpolar. Same with toluene. So notice how 4, 5, and 7 are all similar, and then 6 and 8 are similar because they're both ionic. All right, so that was just one way. Hopefully this was a little better than you trying to just do it on your own at home. I know it's not the same as being in class, but I wanted to give something just to make it a little bit different. So for the rest of the time, there's about 20 minutes left. Thank you guys for bearing with me as we tried some of these new things today. I definitely would like to hear what you think about this. So whether you send me a reminder or you type it in the chat, whether something like this is useful if we're doing, more conceptual ideas like this. But you'll see the to-do list. We've now marked 3 of the 4 things off. So you watched the video and took notes. We went through some examples in the notes. We did page 4. And now you have time to work on mastering. So you have time. You can go through 1 through 14 of mastering. If you would rather use this time to get the video watched for tomorrow, so video 412 in Edpuzzle that's already up, you can watch that. I noticed that some people were watching that after they finished with the first one. And then again, just some reminders. The e-text, if you do want the e-textbook, those sections of the textbook are within mastering. They're hyperlinked in mastering. And then I was recording this second section, and that will get put up onto the playlist for Unit 4, probably during 5th period today. So I'm going to end this just so that we've kind of gone through it. Okay. And you guys now just have time to work. So if you want to stay on the Meet, and that way if you have questions, you can hop back on. If you'd rather just leave the Meet and work on mastering, you can. But that's all I have for today. Tomorrow, you'll have more time to work on mastering. So you'll definitely have more time tomorrow because I don't foresee tomorrow taking as long either. But that's it for today.